Welcome back to the class Computational Neuroscience, Neuronal Dynamics of Cognition. In order to continue with our discussion of field models, we now have to look at transient. So our first mathematical aim is to go beyond the stationary state, focus on transients, focus on the dynamics. And it turns out that in this case, the neuron model matters. And therefore, I have to tell you a little bit about integrate and fire neuron models. So in the integrate and fire model, I have a linear differential equation, and I can visualize this dynamics as an RC circuit. And each time that a spike arrives, a little charge is put on the capacitor, and the result is that the membrane potential goes up, and then it decays exponentially. So this is the response to a single pulse. If I have many input pulses, then I would simply add up these different responses, and then finally out goes a spike. Now, the spike is emitted at the moment of threshold crossing, and afterwards we reset to a lower value and the whole process starts again. So there's a slightly different way of looking at this, and this is to say, well, each input spike causes an excitatory postsynaptic potential, EPSP. If you have several input spikes, we add them up until we hit the threshold. And then instead of the reset, we say, okay, we paste in the spike, and importantly, we paste in this spike after potential. So we replace the reset by an equivalent formulation, which is we add a spike after potential, we add something negative to bring the potential down again. So in a schematic view, we arrive at the following picture. I have an arbitrary input current. It's filtered. This gives rise to the membrane potential. If you hit the threshold, out goes a spike. And then these spikes contribute a negative part of the membrane potential, which I have to add in back here. So the total membrane potential is the effect of this negative feedback, the spike after potential, caused by the spikes, and the effect of the input itself. So this is what I call h of t. This is what I call the input potential, the part of the potential that's caused by the input. Now there's one more thing I would like to say, and that is normally in an integrate and fire model we would have a strict threshold crossing criterion for a spike. However, we can loosen this criterion. For example, we may say that we look at the momentary distance between the membrane potential and the threshold. And if this distance, u of t minus theta, is small, then there's already a certain likelihood to fire, even though the membrane potential has not yet reached formally the threshold. For example, if u of t is just 1 millivolt below threshold, so I would have and if delta is 1 millivolt, I would have here e to the minus 1, which is already a certain firing rate, a certain instantaneous rate, a certain instantaneous probability of firing. So this parameter, delta, describes the softness of the threshold. If delta is 0.01 millivolt, then it's basically back. We are back to a threshold crossing. If delta is 2 millivolt or 5 millivolt, it's very noisy. We have a high noise threshold model. So the trick for the following is to separate this total membrane potential in these two components, a part that's caused by the input and a part that's caused by the feedback. So if you go back to the leaky integrate and fire model, we have a linear differential equation. I will now use this to separate out the input potential from the reset part. So the way we do this is to say, well, this input current is really the current caused by the input, external input, plus it's a current that's caused by the reset. It's the internal currents, the ion currents generated in the neuron that cause the reset. And since it's a linear differential equation, I can just integrate up the two parts separately, and I will just focus on this external input part. And since it's only one contribution, I rewrite the differential equation now with the new variable h which is the same equation, but I just focus now on this part of the input. And I can integrate this up, and I get an h of t, which is I external of t minus s, and I integrate over s with an exponential filter 1 over tau in the exponent. Now, I need to have the units correct, and the way to do this is to write here r over tau. Tau is rc, so this would also be a 1 over c, 1 over the capacitance of the RC circuit. So I can write this h of t as some filter, kappa of s, I of t minus s ds, and the integral runs from 0 over infinity. And this is the input potential. Now, I don't know the exact reset currents, but if I knew the reset currents, then I could sort of redo the same calculation and arrive at the reset potential, and then I add the resting potential from up here, and I'm done. Because it's a linear differential equation, I can add up the solutions. So the total membrane potential is the input potential, which I'll call h of t, plus the reset potential, plus the rest. So here again, the summary slide. I have my external input. I put it through a filter. The filter would be the exponential filter, but it can be something else. But for the standard leaky integrator, it's just an exponential filter. After integration, I have the input potential. It's up here. I compare with a threshold, either the noisy way or the deterministic fashion. And then I have my reset contributions, which I did not calculate for you, but that would give rise to the reset potential. You can also think of this as the drive of the neuron. This drives the neuron. And this you can think of as reset potential as the potential shaping the gain function. If I have a neuron with strong refractoriness, with a strong reset, with a prolonged, temporarily long spike after potential, then the gain function will have a lower firing rate at the maximum than if the reset is very small and if there is no additional refractoriness. So now we have some basic ideas about inputs and about the input potential. And the question now is, suppose I have my population here, population of 500 neurons, or 1,000 neurons, or 5,000 neurons. It is a big population, and all neurons are of the same type. For the moment, we don't have any coupling. They are uncoupled neurons. And now I drive these neurons with a certain input current. This is now my external input. It would give rise to this input potential, which is the low-pass filtered version. And the question I now have for you is, do you expect this population activity, if I do my standard way of calculating the population activity, do you expect this population activity to follow the input current? Or do you expect this to follow the input potential, in which case it would be low-pass filtered? Or you could say, well, maybe it's even low-pass filtered twice, because it will approach this new value only with an additional time constant tau. Or going the other direction, you could say, well, maybe it doesn't follow the current, but it's as fast as a current step, but then it will decay down again, in which case it would be a function of I of t and I prime. So the question I have for you, which model would you choose? Here are the 4 models. Well, let's look at simulations. So the idea is that we model interacting populations. Through the retina, there's some input while the person is watching a video. So the images will change 2 or 3 times per second, and information is transmitted through different populations. I will focus on one of these populations, and I will simulate this population of 50,000 neurons, 40,000 excitatory neurons, 10,000 inhibitory neurons. And now, because the input switches from time to time, at some point the input rate to this population will change. And here's how it looks like. I have here my population of 50,000 neurons. If I average over all neurons, I see the population activity, which is flat here. This is the moment when I switch the input, and then the population activity is higher. Now, importantly, this switch is super fast. It's super fast. I don't have this low-pass filter of the input potential. If you look at one of the neurons, this neuron here, you see the red spikes here, that's this neuron. If you look at this membrane potential, it fluctuates here, and then once I do the switch, it integrates up. Here you see the low-pass filter. However, the population as a whole is much faster than this specific neuron. Now, the reason is that in a population of spiking neurons, where some neurons are always active, there are some neurons that have a membrane potential just below threshold. And when I switch the input, these neurons will fire immediately. So, this simulation shows the population activity can react super rapidly to a change in input. Transients can be fast. Here's an additional simulation. The red line gives the exact theory that we can predict that I would like to discuss. The black line is the simulation. And you see that for these generalized endocrine fire models, also called spike response model neurons, with escape noise, if I have a low noise value, then the response is super fast. So it's a little bit like this response to the input current, except that we have these additional transient oscillations. This is for low noise. Now, if I'm in the high noise limit, then the response of the population is slow. It follows more or less this input potential h of t. So, in this high noise limit, we have slow transients. And if I have slow transients, I mean I can describe the population activity as a function of the momentary value of h of t. So h of t increases slowly after the change in the input, and the population activity also follows slowly. So if we have these slow transients, I can use that the population activity follows the membrane potential. Now we have seen that the input potential itself is described for endocrine fire neurons by this kind of differential equation. And now we can exploit that if I have a network of connected neurons, that this input current will have a part that's really coming from the activity inside the network. This activity of this network activity will be A of t. So this external input, this total input, will be input coming into the neurons from neurons in the same population. And we have seen that this kind of input would be proportional to Q times A of t. And then there will be sort of true external input coming from other populations. And I describe this as I outside, coming from outside this specific population. So a neuron in this network would follow this differential equation with R times QA of t. So the neuron is driven by the population activity, and the input potential represents a low-pass filter version of this population activity, plus the input from other sources outside this population. Now let me do one more step. I will use this equation here and plug it into this A of t. So A of t itself is a function of h of t. Let's call this gamma. I copy the rest, minus h of t plus gamma times f of h of t plus r times I outside, input coming from other sides. And I copy the left-hand side, h of t. So now I have a differential equation where I have a h of t on the left-hand side, d dt h of t. I have a h of t here, and I have a h of t there. So we have one differential equation for one population. At the moment I have one single population. To arrive at this closed form with just one differential equation, it was important that we used our assumption of slow transients, which means we assumed that we are in the high noise regime. So here's again the summary. In the high noise regime, I can always describe the population activity as a function of the input potential. For the input potential, I have a differential equation. I plug in my input current and have, in the end, one differential equation for one population. So let me summarize what we have seen. I've derived a population activity equation, and we see that this population activity equation has smooth transients. It has smooth transients because the population activity reflects the input potential, or to put it differently, the input potential determines the activity. But this is valid only in the high noise limit. It misses the sharp transients that we would see at low noise, and it misses the transient oscillations that we will see in spiking neurons working in the low noise regime. Before we continue, please have a look at the quiz.